Okay, welcome back, everybody. We're going to start our next session, which is about resilient NEXTHOPs. Hopefully, you had a good break. Ido and Petr are going to walk us through the work that they've been doing. This is actually a fairly important and required step to making Linux networking the core of how data centers and failover and resiliency is built. So we're going to do the usual thing. The video is going to run for 30 minutes, and then we're going to bring Petr and Ido back for questions. And if you have an emergency question you need to ask, do raise your hand. But otherwise, ask your questions in the Q&A tab, and we'll get to it at the end. So without further ado.
Hello, this is Petr Machata. I'm here with Ido Schimmel, and we are going to present our work on resilient NEXTHOP groups. First on mic is Ido.
Thanks, Petr. Next slide, please. The agenda for this presentation is to give a short background about multipath routing. Then we will cover the motivation for resilient NEXTHOP groups. Then we will give a short overview of NEXTHOP objects, which is the kernel infrastructures on which resilient NEXTHOP groups is based on. And then we will talk about resilient NEXTHOP groups. We will cover the theory, the implementation, hardware offload testing, and finally, possible future extensions. Next slide, please. A short background about multipath routing. Multipath routing takes place when a router can choose to forward a packet to one out of several routers. In this example, R1 can choose to forward a packet via either R2, R3, or R4. And there are two main components when performing multipath routing. Next slide, please. They are the multipath hash computation, which is needed in order to ensure that all the packets that belong to a certain flow will be forwarded via the same NEXTHOP. And the second one is the NEXTHOP selection algorithm based on the multipath hash that was calculated for the packet. Next slide, please. In Linux, multipath hash calculation is very flexible, and it is controlled separately for IPv4 and IPv6 using these two sysctls that you see below. And you can either choose the policy to be based on 3-tuple, that is the source IP, destination IP, and the IP protocol of the packet, or it can be 5-tuple or a completely custom policy based on a bit mask. After we calculated the multipath hash of the packet, we need to perform NEXTHOP selection. And there are two main algorithms for NEXTHOP selection. The first one being hash threshold, which is the one that is actually implemented in Linux for both IPv4 and IPv6. And in this algorithm, the key space, which is 31 bits in Linux, is divided into regions according to the NEXTHOPs and their weights. At the figure below, you can see that initially we have 5 NEXTHOPs that all have the same weight because they have the same region size. But then after some time, NEXTHOP 3 goes down. And what can happen is that flows that were previously hashed to NEXTHOP number 2 can now be hashed to NEXTHOP number 1. And this is something that we would like to avoid. The second NEXTHOP selection algorithm is called modulo n, where n corresponds to the number of NEXTHOPs in the group. And obviously, when the number of NEXTHOP changes, then we are risking flows being rehashed into different NEXTHOPs. So this modulo n algorithm is more disruptive than the hash threshold algorithm. Next slide, please. The motivation, the primary motivation for resilient NEXTHOP groups is load balancing. Previously, we showed an example where multipath routing is used in order to choose a path out of several paths that eventually all lead to the same destination. But we can also use multipath routing in order to perform load balancing between several servers. So in this example, we have a router R1 that is performing load balancing between 3 different servers, H1, H2, and H3. And initially, we have a flow that is being hashed by this by R1 to the first server. But now let's look what happens when we are increasing the load balancing pool by adding yet another server. Next slide, please. So since we added another server, the flow can now be hashed to, it is possible that the flow will now be hashed to server number 2, because the boundaries between the hash regions changed. And this is something that we would like to avoid. And let's see why. Next slide, please. Since server number 2 is unaware of this established connection, then it will send a TCP reset packet back to the client, causing the connection to be reset. And this is something that is very undesirable. Next slide, please. A short overview about NEXTHOP objects, which, like I previously mentioned, is the kernel infrastructure on which resilient NEXTHOP groups are based on. It was introduced in kernel 5.3 by David Ern, and its main selling points is that NEXTHOP objects are managed separately from routes, unlike in the legacy API that you are mostly familiar with. So on the left, you can see the legacy API, where routes and the associated NEXTHOPs are configured in the same message. But with the new model, with NEXTHOP objects, we can first configure the NEXTHOPs as separate objects and then point route to them by specifying the NEXTHOP ID. Let's look at an example. Let's look at an overview of the interface in the next slide. So here you can see that initially we had 2 single NEXTHOPs whose ID is 1 and ID 2. And then we decide to group them together at a group whose ID is 10. And we can also decide to change the weights of the NEXTHOP, so that now NEXTHOP 1 has a weight of 3 and NEXTHOP 2 has a weight of 5. And obviously we can also retrieve information about the group. And once we are happy with the configuration of our NEXTHOP group, we can decide to point a route to it by specifying the NEXTHOP ID of the group, which is 10 in our case. With regards to the netlink interface, it is following the usual pattern of new, del, and get, where new is used in order to create object or replace object, del is used in order to delete objects, and get is used in order to retrieve information about existing objects. With this, I will let Petr discuss the implementation of resilient NEXTHOP groups in the kernel.
All right, hello. Thank you, Ido. I'm not going to cover this slide. This is purely for, for closed-loop perusal if you care about how this was modeled before. And I will jump to resilient NEXTHOP groups right away. So the idea behind hash threshold is that there are you split the hash space into as many areas as there are NEXTHOPs. And then each NEXTHOP obviously belongs to just one area. So as configuration changes, the only thing that you can do is you change the individual borders. You cannot reassign like bits of the hash space between one NEXTHOP and the other. This is the idea behind the resilient NEXTHOP groups. The idea is that you split the hash space into smaller, more granular, we call them buckets, and then assign NEXTHOPs in general to more than one bucket. So that you have much more buckets than you've got the logical NEXTHOPs. And you can assign on this per bucket level, which allows you to achieve like these irregular shapes where parts of NEXTHOPs are spread over the whole hash space. Then the selection, when you forward packets, then the selection algorithm becomes modulo n, except n now is number of buckets. And then you look into, or actually the algorithm looks into which NEXTHOP is occupied by that bucket. One area where this kind of works splendidly is the NEXTHOP removal. When NEXTHOP is removed, the algorithm simply walks the table, looks which buckets have been occupied by this NEXTHOP, marks them as vacant, and now it recomputes how many buckets each NEXTHOP should have, because that changed. I now have fewer NEXTHOPs, and since we've got 3 vacant buckets and 3 NEXTHOPs, it's kind of obvious that what we do is, or what the algorithm does is, it spreads the NEXTHOPs among the empty buckets. Note that besides the removed NEXTHOP, none of the other NEXTHOPs has, none of the other hash space assignments has changed, right? So only buckets 1, 5, and 9 have changed, and they had to change because they were occupied previously by NEXTHOP that is not active anymore. So there is no incidental damage when removing. It doesn't work quite as well with addition, obviously, because I have now, if I am adding a new NEXTHOP and all the hash space is already obviously spread among the existing NEXTHOPs, I need to take the space, I need to find the hash space to assign to the new NEXTHOP somewhere. So I need to take away from some of the NEXTHOPs. The idea here is that maybe it will be possible to find bits of hash space that are not actually used. And the way this is achieved is that we keep track of when was the last time that each bucket was used. So as the forwarding process is made, as the modulo N chooses one of the buckets, besides looking which NEXTHOP is assigned with that bucket, I also, or actually the algorithm also makes a note that this is the last time that the bucket was used, right? So I know the algorithm now understands which buckets have been used when. And then you have 2 knobs. One is the idle timer, which is the amount of time, how long traffic should not hit a certain bucket to be considered idle, right? So this is the first configuration parameter of the NEXTHOP groups. And if a bucket is considered idle, the algorithm will then consider that bucket when finding more hash space to assign to another NEXTHOP. Now, it might happen that there is no idle bucket right now. So in that case, the algorithm backs off for a while. It finds which bucket might become idle next, sleeps for a while, tries again next time, right? And in this iterative approach, it can gradually migrate the group into a new stable state where every NEXTHOP has as many buckets as it should have according to its weight. Obviously, this depends on traffic patterns, and it might happen that simply there keep being no idle buckets. And then one of 2 things are going to happen. Either you as an administrator are fine with that. Maybe integrity of the flows is more important to you than, let's say, fair use of the equipment. Or you have limited patience, and that is expressed using the other configuration knob, the unbalanced timer, which is the amount of time, how long the algorithm tolerates that the group is out of balance, meaning there are unsatisfied demands for more buckets. And after this timer expires, some of the buckets are going to be reassigned even if they are busy, even if they are not idle. The addition process is illustrated in this illustration. You can see that as previously, we had 12 buckets and 4 NEXTHOPs. We are adding a 5th NEXTHOP. And somehow the algorithm decided that 1 bucket should be taken away from NEXTHOP D and 1 bucket should be taken away from NEXTHOP A. And after some, whatever it is, maybe one of them was idle and maybe one of them was force reassigned, eventually reassigns buckets 3 and 8 to the new NEXTHOP. Again, right, we had to sacrifice something, but we sacrificed only as many buckets as were necessary to fulfill the demand that the new NEXTHOP has a certain weight and should have a certain share of the hash space. Let's look at how this is configured. This should be very familiar. It's the same thing as before, except now since previously there was only 1 NEXTHOP group type. Now there are more, so you need to say that you need the resilient type. So type resilient, and then resilient groups have a bunch of parameters that can all be specified on the command line as well. Number of buckets is kind of obvious. The number 8 that we are showing here in this example is kind of low. Usually you would have like hundreds, let's say. Sometimes, maybe 1K, maybe even 4K. idle timer, unbalanced timer we covered. Since there are now a number of parameters, you can tweak them individually. In the first example, in the change attributes section, you see change of configuration of idle timer. The second example, change of configuration of unbalanced timer. In both of these cases, the remainder of the configuration stays the same. So number of buckets stays the same. That is a constant that always stays the same. But in the first example, the unbalanced timer stays the same. In the second example, the idle timer stays the same. What also stays the same is the distribution of NEXTHOPs among the buckets. And the third example is kind of interesting from this regard because we change weights of the NEXTHOPs. And what that leads to is simply changes in how many buckets each NEXTHOP demands. But it doesn't necessarily mean anything is going to be reassigned just yet, right? So now comes the idle timers and unbalanced timers, stuff like that. Is going to gradually bring the group into this 9/11 configuration. With regards to netlink, we have the usual trifecta of new NEXTHOP, del NEXTHOP, get NEXTHOP, and we have a new one, get NEXTHOP bucket. And on the next slide, we are going to look at introspection. When dumping the group, besides showing the usual attributes, you also learn that the group is resilient, that there are 8 buckets. It shows the other parameters. It also shows unbalanced time, meaning this is the amount of time that the group has been out of balance, meaning there have been unsatisfied demands for more buckets by some of the NEXTHOPs. Some of the NEXTHOPs are underweight. And since this is showing 0, it means the group is actually balanced now. And the new NEXTHOP, the new netlink message is used for dumping the individual buckets. So you can show, you can do IP NEXTHOP bucket show, and it shows the bucket table associated with this NEXTHOP group. It shows the idle time of the individual buckets, meaning how long has it been since it saw traffic. It shows which NEXTHOP is mapped into that bucket, and it shows flags if there are any, right? Offloaded or trap. Like before, I'm not going to cover this. This is for closer perusal if you care about this stuff. Let's talk about hardware offload. It says here, NEXTHOP bucket activity idleness is a key parameter to ensure resiliency. So what he's trying to say is that the algorithm hinges on the fact that it understands which bits of the hash space are used and which aren't. And this is easy to do in the user space because, I mean, not user space, but software data path. And because as the algorithm makes the forwarding decision, it can also make note of which buckets are used. But with hardware data path, you know, the traffic is not seen, so we need something else. And we've got a two-pronged approach to fixing this. The first is that the NEXTHOP code actually forms the bucket migration changes as proposals. So if it decides that buckets such and such should go from the NEXTHOP that it currently has to another NEXTHOP, it makes a notification. The driver catches this notification and pushes it to the hardware. And the hardware can say, no, don't do that. There has been traffic actually going on. And then the driver can veto actually the proposal by the NEXTHOP code, which makes note of the fact and looks for another bucket. And that would work, except it would be very inefficient because there would be a lot of ping pong because since like vast majority of the traffic is in the hardware, the NEXTHOP code would think that basically everybody is idle and would keep proposing these migrations and the hardware will keep bouncing them. So this is not a very efficient way of achieving the functionality. So instead we've got this. So we have this because this closes some loopholes, but we also have a new function called NEXTHOP REST group activity update, which is an API in the NEXTHOP code, which drivers use. The idea is that the driver periodically polls the hardware for busyness information about the individual buckets, composes it into a bit vector, and feeds this bit vector into the function that I just mentioned. And then the NEXTHOP code takes a look at the bit vector, and for every one that is set in the bit vector, it hits the corresponding bucket with traffic, sort of, right? It marks the bucket as used with the last used time now. And besides, you know, now that the algorithm has a better understanding of what traffic actually looks like down there, besides not making a number of stupid proposals about migrations that they're never going to fly, it can also tell this information to the user space. So when the user space is dumping the information about the table, is going to have a closer understanding of what's actually going on down there. Okay, let's talk about testing. So the hash threshold algorithm is stateless, which is to say not that there are not any data structures, but that if the hash thresholds have been recomputed every time traffic is forwarded, it would work just as well. It would be, obviously performance would be horrible, but it would work because the computation is pure. But for the resident NEXTHOP groups, there is a lot of state, right? At least it all depends on traffic patterns, because those impact how the idleness will look like, and then it needs to keep track of the timers and the gradual migration process. So it is kind of much more complex problem to test, and we want to make sure that it actually works. That it actually, the stuff that we think it's doing it's actually doing. So there are a number of new tests. The FibNet NEXTHOPS SH, the first test that is mentioned, is an API test. So it already had a bunch of tests for NEXTHOP code. So we added new ones for specifically resident NEXTHOP groups. The router empath and GRE multipath tests have been there before. So they were adapted for resident NEXTHOP groups. So there are now two flavors of the test, one for normal hash threshold NEXTHOP groups and one for resident NEXTHOP groups. One thing that might make sense to do is describe the new attributes to syscaller so that we can fuzz this stuff, but we have not done that. So maybe if you want to do that, go ahead. And let's talk some more about testing. So in particular, because of the statefulness of the algorithm, it's kind of tricky to make sure that some edge cases are going to be handled correctly. And so we ended up writing a Netdev sim offloader for the resident NEXTHOP groups. And besides just exercising these APIs, it also exposes debugfs API that user space can use to toggle busyness of a certain bucket. And this is used in testing for stuff like, let's see what happens if we mark all the buckets that belong to a certain NEXTHOP. Let's mark them as active, and then change the weight and see how it handles, the idle timers and the unbalanced timers, stuff like that. So it's super, super useful for testing all sorts of edge cases. All right, I believe this is it from me. It is going to talk some more about future extensions.
Thanks, Petr. Okay, so now I will cover a few future extensions that we considered. And I would like to mention that we do not have a concrete use case for any of those, but we did consider them during the design phase in order to ensure that our design is future-proof. The first extension is group consolidation, which can be used in order to reduce resource usage by consolidating identical NEXTHOP groups. Let's look at an example. Here we have two NEXTHOP groups, ID 10 and ID 20, and they are identical because they are made up out of the same logical NEXTHOPs, 1, 2, 3, and 4. And we have several routes pointing to each group. But we do not need to have these two identical NEXTHOP groups. We can have all the routes that are pointing to NEXTHOP group 20 point to NEXTHOP group 10 and then delete NEXTHOP group 20. At least in the case of hardware offload, this allows us to save 4 adjacency entries, which is not very considerable, but let's look at the next slide. So here we have a resilient NEXTHOP group. Yeah, sorry. So here we have a resilient NEXTHOP group, which is not made up out of only 4 adjacency entries, but rather 4K adjacency entries, because its size of the bucket table is 4K. And reducing the resource usage by 4K entries becomes significant. And it's important to mention that in case user space or routing daemons, if they want to consolidate a resilient NEXTHOP group, then they need to make sure that they are identical at the bucket level and not only at the logical level. Because if they are consolidating two NEXTHOP groups that have the same logical NEXTHOPs but have differences in their bucket table, then they are risking some flows being reset during this consolidation. Next slide, please. So really, you can already perform this group consolidation today. You do not need any special API. But if you have millions of routes pointing to each NEXTHOP group, then consolidating the groups means that you need to send millions of route replaced netlink messages to the kernel, which is quite inefficient. But we can make use of the fact that the kernel already knows which routes use which NEXTHOP object. So instead, we can extend the user API and basically tell the kernel, walk all the routes that are pointing to NEXTHOP object X and have them point to NEXTHOP object Y. And then we can delete NEXTHOP object X. So this allows us to reduce the number of messages that are exchanged between user space and the kernel from millions of messages to a single message. But we can also reduce the number of messages that are exchanged between the device driver and the device, because switch ASICs usually have the ability to perform such replacements atomically. Next slide, please. Another future extension is static resilient NEXTHOP groups. In the current implementation of resilient groups, NEXTHOP objects can be dynamically mapped by the kernel to NEXTHOP buckets, which basically means that a NEXTHOP bucket can transition from any NEXTHOP object to any NEXTHOP object. And this is usually fine, but it becomes problematic when state is shared between a subset of our NEXTHOPs. In the example below, you can see that state is shared between NEXTHOP IDs 1, 2, and 3, and also between NEXTHOPs 4, 5, and 6. Next slide, please. Now let's look at this NEXTHOP group at the bucket level. So we have the same logical NEXTHOPs from before, 1 to 6, and our bucket table has 12 buckets. And you can see that initially the bucket table is evenly split between the two subgroups, the blue group and the red group. But when NEXTHOP 1 goes down, then the kernel can choose to replace its buckets with any NEXTHOP ID it wants. So in this example, you can see that bucket number 0 was populated with NEXTHOP ID 4, and bucket number 6 was populated with NEXTHOP ID number 5, which belong to a different group. They belong to the red group. So we are basically risking any flows that were hashed to these two buckets, 0 and 6, from being reset since NEXTHOP 1 went down. Next slide, please. So the mitigation that we propose is to add another mode for resilient NEXTHOP groups, a static mode, where user space can determine the mapping between NEXTHOP objects to NEXTHOP buckets. And we allow user space to color different buckets by assigning them to banks. And when a NEXTHOP goes down, the kernel will only repopulate the NEXTHOP buckets according to their bank. Let's look at the previous example. So again, initially we have the same 6 logical NEXTHOPs that are evenly split between the 12 hash buckets. And you can see that the NEXTHOP IDs that belong to the blue group are annotated with bank number 1, and the red group has bank number 2. And now when NEXTHOP ID goes down, the kernel will only try to repopulate it with NEXTHOPs that belong to the same subgroup, to the same bank. In this case, you can see that bank number 0 was populated with NEXTHOP ID 1 and NEXTHOP ID 2 from bank number 1, while bucket number 6 was repopulated with NEXTHOP ID number 3 that also belongs to bank number 1. Next slide, please. And this is an overview of the proposed command line interface. So you can see that you configure a resilient NEXTHOP group as usual, with the sole difference of saying that its mode is static instead of the default dynamic mode. And then you can start associating the buckets with the desired NEXTHOP IDs and also specify the bank. In our example, we only have 2 banks, bank number 1 and bank number 2. Next slide, please. The final future extension is FRR support. FRR already has upstream support for NEXTHOP objects since version 7.3. And adding support for resilient NEXTHOP objects should be quite trivial, given that all the heavy lifting is performed by the kernel. So this is definitely something that we expect to see in the future. That's all, and please let us know if you have any questions. Thank you.
Thank you, Ido and Petr. We are open for questions. There is one, so let's just jump to that.
Yeah. Can you hear me?
Yeah.
So this feature was requested by at least 2 users that I know of, and I think that another user mentioned it on the mailing list. And I don't know the exact state where they are at, but either they already deployed it or they are in the testing phase.
I would add a sentence to that, right? Which is this feature is very widely used in commercial nozzles. The equivalency into Linux is what this thing is bringing up. And in fact, as you noted, the switches, the devices underneath have been doing this for a very long time. This is just an exposure from a software interface perspective. So if the question is really about, is this on SwitchDev or using Linux as a hook being used, then I guess Ido's answer is right. If not, it is a widely deployed feature.
Yeah, I assume that the question was regarding the Linux implementation.
Okay, I guess the next one is me as well, but it looked, well, there were more questions here. Hang on. Let's go with this one. Yeah, David said, yes, Linux inspector. Okay. Do you see this one, Ido, Petr?
It seems that you have mixed up a stateful mechanism. So, I mean, this implementation is used in order to replace a lot of very expensive load balancers where, from what I understand, you are paying the vendor based on the bandwidth. And like ECMP is stateless, which is why it is very efficient at forwarding high bandwidths of traffic. So, like, I mean, there are situations where this mechanism is not effective. For example, if you want to withdraw a load balancer gracefully from the load balancing pool, then this is not something that you can do with only the switch, only changes on the switch. You need some cooperation between both the host and the switch. And we actually implemented something similar based on what Fastly did with their FailD algorithm. But instead of using a dedicated kernel module, like they mentioned in their article that I will paste, we did it with XDP on the host. So like, I don't really see a question. I think it's mainly a comment.
Michael, any follow-up? Is that good? Okay, I guess we'll call that answered. And the last one was another comment from me, which is the static seems like it's really not static, right? Static implies that I've already picked my paths in some interesting way. This is really more banked, right? So maybe make the mode be like a banked NEXTHOP or something, because it's a hierarchy you're building, right? Which and says pick within these group or pick your group within these particular links. So maybe using a term like that is more meaningful than dynamic versus static. Okay, Michael seems to want to come back, so I'm going to bring him back on. And Jamal is here as well.
Hi. Sorry, I couldn't find the raise hand button very quickly. It's hidden if you make your windows too small. So my question is, like, what are you trying to solve a stateful problem with load balancing? Because usually the thing is you keep the session going, the TCP session going with whatever target was there, and then you can make new decisions, but you do that because you have a 5-tuple flow switch. And so you seem to have thrown that away or not bothered to implement it, or I'm not sure. So I don't understand why you're concerned for it, because I don't think your solution can be very well used for load balancers to begin with. So maybe just focus on ECMP. Like, that's a really good thing to me.
Like this is ECMP, but with a bit of resiliency when a server goes down or a server is added.
But you said server, and you started off talking about routers. So I understand routers go down, and then you just reroute the traffic, and that's really good. But if servers go down, that's stateful dead, right? I mean, of course, you're going to get a TCP reset at that point if the server goes down.
Yeah, but you will only get a reset for the server that went down, but it will not affect connections going into other servers. But with regular ECMP, it will affect everyone.
Because you're going to rebalance everywhere.
Yeah.
Yeah, so that just seems to me like that's what I'm trying to say. You're trying to apply an ECMP method to what's really supposed to be a stateful routing process.
Stateless. I think that maybe it's worth explaining the use case, right? The use case is you are a router.
I didn't understand. Yeah,
it's a router connected to 10 servers. And the case
is it, or is it a router connected to 10 routers?
No, it's a router connected to 10 servers.
Yeah, well, it's the last
seems like you're at the beginning that you forgot that it has to be stateful. I mean, I built boxes, hardware 20 years ago that did this, and it's got to be stateful, and no one wants to buy something that's not stateful. And it's stupid, right? Because they could just use routing with 10 different IP addresses, but they don't do that for reasons that still elude me.
Michael, there are different ways people have built that, right? So, I mean, you're suggesting one. There are other ways in which I can do multiple paths into endpoints that then route into underlay networks. And
of course. Right? And that makes total sense to me, right? And there's lots of other ways of things like, oops, this is the wrong packet for the wrong device. I'll just forward it because obviously the hash table hasn't worked out yet, right? There's lots of people doing this. I'm just trying to understand what is the use case, because it started off with a picture about routers and then suddenly it became servers, and then you're worried about TCP reset. And so I'm like, well, it seems like if you were worried about TCP reset, then you needed to start with that assumption rather than end with it, right? I think it's really good work. I think it's really interesting work. I just don't think that it applies very well to load balancers. That's what I'm trying to say.
I mean, the comment is about the flow of the slides, or I mean, because multipath routing can be used in either to load balance between multiple paths that are all going to the same server eventually, or between different servers, which is the primary motivation for resilient NEXTHOP groups. And like I mentioned, completely replacing stateful and very expensive load balancers has advantages and disadvantages. But for some use cases, people obviously would prefer to use stateless boxes in order to approximate a stateful load balancer. And like someone also mentioned in the comments, it can also be used as a first stage in a load balancing cluster.
Okay, looks like we have a raised hand. Hang on. Christian wants to say something.
Yeah, 20 years ago, I wrote 2992. I'm just happy to see this work come to Linux 20 years later as building, making that much better. So thanks for the work.
Yeah, I think you were at the last Netdev as well, and we talked about it. So yeah, your RFC is widely used in Linux since 2015, I think, and we merely improved upon it.
Yeah, it's great. Great work. Thanks. That's it.
Okay, I'm not seeing any more unanswered questions. If anybody has any last minute, now would be a good time to ask. If not, thank you. As has been noted, this is really good and really good to see Linux catch up here.
Right.
Thanks,
Thank you.
Petr and Ido.
Thank you.